Hey, it's Mr. Beck. We're going to step through a bunch of multiple choice problems. If you haven't already downloaded and tried these on your own, or if you don't have access to that document, maybe you can just pause and look at each one of these problems, see if you can solve it by yourself before listening to my solution. So here we're given three objects, x, y, and z, and they're given some excess electric charge. So I have three charged objects. Then they're brought near each other in pairs, but do not touch. That means that they're not going to exchange any of their charge with one another. And it's found that x and y attract each other. So let me draw an attractive force, meaning x is being attracted to y to the right, y is being attracted to x to the left. Y and Z repel, so that means between Y and Z, there's a force on Y away from Z and a force on Z away from Y. And then X and Z attract. So Z is attracted to X and X is attracted to Z. And it's asking about which is the correct conclusion about the signs of the charges that can be drawn from these observations. Well, take a look at that, X and Y and Z. You'll notice that Z and Y are repelling each other, so that means that Z and Y have to be opposite charge, have to be the like charges because like charges repel. And then X is attracted to Y, opposite charges attract, X is attracted to Z. So X is attracted to both Y and Z. That means that X must be one type of charge, and then Y and Z must be the same charge, but different than X. So I don't know which is positive or negative, but we know that X is one type of charge. So let me just color that red for a moment. And then Y and Z are a different type of charge. So let's color both of those blue. Does that make sense? So that X and Y are attracted, so the red and the blue attract. X and Z are attracted, the red and the blue attract. But Y and Z repel, the blue and the blue repel each other. So now let's look at the options. X and Y have charges of the same sign. Nope, that's not going to be correct because we know that X and Y are different. So we can get rid of option A. X and Z have charges of the same sign. Nope, we already determined that those are going to be opposite, so that's not going to be correct. Y and Z have charges of the same sign. We colored Y and Z blue, so far that's good. And X has a charge of opposite sign. That sounds like a pretty good solution so far. And here, X, Y, and Z all have charges of the same sign. No, we've determined X is different than Y and Z, so that one is wrong. So the answer to this problem is C. All right, this next problem, which is question number 15, obviously, says a particle with charge Q, so let me just write down that Q, and mass M, so that's the particle, there it is, has an instantaneous speed U1. It's U instead of V because they want V for voltage. So we'll just, whichever direction it's going doesn't matter. We'll call that U1. When it is at a position where the electric potential is V1. So let's write that as V1. At a later time, the particle has moved a distance r away. So let's move to a new place here where this is capital R. That's my new location, where the electric potential is V2. Which of the following equations can be used to find the speed U2 of the particle at the new position? So at this position, it's going to be U2. And what we have here is going to be a conservation of energy sort of problem. So at the first position, position 1, the charge is going to have a certain kinetic energy and a certain potential energy. And the same thing at position 2, it's going to have some potential and kinetic energy. So what I know is that the potential energy initially, well, which I'll call U1, plus the kinetic energy initially, which I'll call K1, is going to equal the potential energy later plus the kinetic energy later. Now, potential energy, when we're using a point charge, the point charge, if we know the electric potential, we know that the potential energy is going to equal the charge times the electric potential. So U is Q times V. So we can substitute that here, and we can say that Q times V1 on the left plus the kinetic energy, and kinetic energy, of course, is 1/2 times the mass times the initial velocity, which here is u1 squared, is going to equal Q times V2 plus 1/2 the mass times the new velocity, u2 squared. Now we can already see in the equation that they give us, they all seem to have the mass on the left and the charge on the right in some way, shape, or form. So we can arrange it so that we have masses on the left and charges on the right. But we also see U2 minus U1. So I'm going to actually go backwards on these, and I'm going to subtract QV2 from both sides, and I'm going to subtract 1/2 MU1 squared from both sides. So that means that I'm going to have QV1 minus QV2 equals 1/2 MU1 squared minus, oh sorry, that's U2 over here on the right, minus 1/2 MU1 squared. So I subtracted this and brought it over here, and I subtracted this one and brought it over to the left. Now you can see that Q can factor out, so I've got Q times V1 minus V2 is going to equal, I can factor out 1/2 M from the other side, 1/2 M times U2 squared minus U1 squared. Now if I look at my equations, actually that first one is 1/2 of M times parentheses U2 squared minus U1 squared. Well, that's what I have over here on the right, equal to Q times V1 minus V2, which is actually what they have over here on the right, is what I have over here on the left. So that's looking really good. But it's going to be helpful to take a look at the other ones. What's wrong with the other ones? Well, I have the V1 and the V2, but here it's just U2 minus U1 squared, but that's not going to be the same, so you can't just subtract the velocities then square it. It's going to be the difference between the squares of the velocities, so that's where that problem got wrong. This one is just saying that 1/2 MU2 squared equals QV1, but it's going to be not just the initial potential, but it's the difference in the potential. This would assume that the potential at 2 is 0 and that the initial velocity was 0. So if you did have an initial velocity of 0 and a final potential of 0, then it would simplify into that. But we know that it has some initial velocity, so that is definitely not the case. And the last one uses this 1/4 pi epsilon naught, and that's actually the same as K. So this is KQ squared over R. So again, this is pretty much the same as Q times V1, but it's also got a squared in there, and so this is just the wrong equation altogether, because this is trying to find the electric potential energy between two different charges, and here we only have a single charge that we're moving from place to place. So this is clearly not the problem either, not the answer either. So this is going to be answer A, this multiple choice problem. All right, the next three problems, 16, 17, and 18, we're going to be working with this same capacitor circuit. So what we have is a 10-volt battery, 10-volt power supply, that's going to send current around, so it's going to come out of the positive and back into the negative. That current, we have a 50 ohm resistor and then a junction. From that junction, we could have current flowing in two different directions, through the 100 ohm resistor or onto the capacitor. And then whatever current's coming from both of those is going to combine back together and go back to the battery. So this says that blah, 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 the circuit has been connected for a long time. Now, if it's been connected for a long time, what that means is that the capacitor will have fully charged at that point in time. So I like to say that initially a capacitor acts like a wire, so the current's going to flow greatly easily onto the capacitor initially. And then later on, the capacitor is going to act like an open switch where it's not going to have any current flowing because it's fully charged and it's going to be at a whatever voltage it's going to get up to. So first we say let I1 be the current in ammeter A1 or AI. That's weird. That actually should be I1 and A1. Which of the following correctly ranks the currents in the three ammeters? Well, we know that the capacitor is now fully charged, so that there's going to be no current in ammeter 2. So this is going to be reading 0. What that means is that all the current is going to be flowing through A1. None of it is going to be going down that junction, and all of the current is going to be flowing through A3 and then back along this path, because this capacitor is going to act as if it's not even there, as if it's an open switch, an open part of the circuit. So what that means is that the current in ammeter 1 and the current in ammeter 3 are going to be equal, and the current in ammeter 2 is going to equal 0. So that means that I1 is going to equal I3, and they're going to be greater than I2, which is 0. So that looks like answer A is going to be the valid answer for that problem. Now we're using the same circuit, the same setup, but now it's asking which of the following is correct about the voltage across the capacitor. So the voltage across the capacitor, in this case, if I were to hook up a voltmeter here and measure across the capacitor, it's going to be the same as if I measured a voltmeter across this resistor, because you can see I could follow the edge of that voltmeter up and around to the top of this, and this is all going to be at the same voltage because it's just a wire. And then the bottom is all going to be at the same voltage. We can ignore the ammeter for now. And the bottom is going to be all at a second voltage because it's all along a wire. So know the voltage across the capacitor is going to be the voltage across the 100 ohm resistor. So now, which is correct about the voltage across the capacitor? Well, it's not going to equal 0, so I know that answer A is going to be wrong. Now it's saying that the voltage of the capacitor is somewhere between 0 and 10 volts. Now, you can see if I started at the top of the battery, then I'll be at 10 volts. The bottom of the battery will say is at 0. Well, that voltage is going to drop across the 50 ohm resistor. So if I had a voltmeter there, it's going to read part of that. And then the rest of the voltage is going to drop across the 100 ohm resistor. So what I know is that the voltage across the 50 ohm resistor plus the voltage across the 100 ohm resistor is going to equal the voltage of the battery. And so since the voltage of the battery is 10 volts, then I know that the voltage across the 50 and the voltage across the 100 is going to add up to 10 volts. Now, we already determined that the voltage across the capacitor is the same as the voltage across the 100. So I know that, the voltage across the 50 plus the voltage across the capacitor is going to equal 10 volts. And therefore, the voltage of the capacitor is going to be somewhere between 0 and 10 volts. So answer B is looking pretty good right now. Here, question C says, or option C says the voltage of the capacitor equals 10 volts. That's not true because some of the voltage is going to drop across the 50 ohm resistor. So that is a bad answer. And then D says the voltage of the capacitor is greater than 10 volts. Well, nothing in the circuit can be greater than 10 volts because I only go up to 10 and down to 0. So there's no way to get above 10 volts. So D is wrong. So for question 17, the answer is going to be B. Now question 18 says, assume the capacitance of the capacitor is known. So let's just write that as C0. We know the initial capacitance. And now the gap between the capacitor's plates is filled with an unknown insulating material. So what's that going to do? Well, normally when a capacitor is charged, we've got a positive, say, top plate and a negative bottom plate, and they're going to set up electric field, but it has to do with how much those positives and negatives are attracting each other. That is about how much charge can build up on those plates. If I place a material in between, an insulating material, what's going to happen is that the material is going to be slightly polarized. So throughout the material, that's going to allow a little bit of charge separation. And with that little bit of charge separation, now I've got charges that are much closer, so the attraction is much stronger, and that's actually going to allow some additional charge to build up on the capacitor itself because it's almost like the plates are closer together. It allows more charge to build up on the capacitor. And the equation for the charge on a capacitor, or for the capacitance of a capacitor, is K, this dielectric constant, times epsilon naught, which is the how well a vacuum transmits the electric field, times the area divided by the distance. And so what we do is we have a new capacitor, basically, which now will have a dielectric in it in this new circuit, where epsilon naught A and over D are all going to be the same. So what we're doing is we're effectively changing the capacitance. And so if we have some way of measuring the new capacitance as opposed to the initial capacitance, then we can figure out what indeed K is, which is what we're looking for. We're looking for the dielectric constant. So in this circuit, what we're looking for is what can we measure in order to determine the capacitance of the new capacitor. Now, once this circuit has been running for a long time, again, we're going to get to the state where the capacitor is fully charged. So it's going to be as if this is no longer even in the branch of the circuit. So the current is going to be running, and the voltage drop is going to drop across the 50, and the current's going to run along this branch, and there's going to be another voltage drop across the 100, and then the current's going to come back to the bottom of the battery. So what we have is pretty much the circuit is going to look identical as it did before. So we need to measure something about the capacitor itself and not just currents and voltages elsewhere. So option A is the potential difference across the capacitor. Well, that we know from before, and it's going to be the same as it was before the dielectric was placed there. And the current in each branch of the circuit, well, those are also going to be the same as they were before. So A is not telling us anything new. B says the potential difference across the capacitor and the charge on one of its plates. Well, this is directly measuring something about the capacitor. It's measuring V and it's measuring Q. And we know that the capacitance is going to be how much charge is stored when I have some amount of voltage. And we already know what the voltage is. Actually, if we measure the potential difference across the capacitor, we're getting that again, which we could have calculated from the initial circuit. But now we know the charge, and with the voltage and the charge, we can indeed find the new capacitance, and that would let us calculate what K is, because we knew the initial capacitance from the previous thing. It says that we know the capacitance of the capacitor initially. So we can compare C to the initial capacitance and we can get what the K must be. So B is looking like a pretty good option here. Number C says the potential difference across the capacitor and the charge on the dielectric material. Now that sounds interesting, but we don't have an equation that tells us anything about how the charge on the dielectric material is going to affect the charge on the capacitor directly. So I don't think that's going to be incredibly useful, or at least not as useful as B. And D says the separation between the capacitor plates and the area of the plates. So that's giving me D and A, but that won't give me the new capacitance of the circuit itself. So that won't help me solve for the unknown K. So our answer here is going to be answer B. All right, this one's a little different. Question number 20. We have two charged concentric conducting shells. So we have conductors here with radii R1 and R2. The space between the shells is filled with air. The dashed lines represent equipotentials, locations of equal potential. The electric field just outside the inner shell has magnitude E1. Electric field just inside the outer shell has a magnitude E2. So right here, I can say I've got electric field 1. And right here, I've got electric field 2. Which of the following is true about the magnitude of the electric field at point P? So we're looking in between. Now, when you have a shell, a conducting shell, if that's all you have, then you're going to have a zero electric field inside. The charges are going to rearrange so that I'm going to have no electric field inside because all of the electric charge is going to be on the outside of the conductor, and when you take a look at the entire surface, it's just going to cancel out. So as soon as I get outside, then the entire charge is going to behave as if it were at the center, and therefore, if all the charge on the shell was at the center, then the electric field at this point, just outside that conducting sphere, is going to be K times Q divided by R squared. So that would be the electric field just outside the inside one. Now, if I had just the outer shell, then outside I'm going to get some electric field, but inside there's going to be no contribution for the electric field from the outer shell. So knowing that, if I take a look here at E2, E2 is just inside the outer shell, so it's almost as if the outer shell doesn't exist at all. So what we're dealing with is only the electric field from the charge on the inner shell here, on the inner sphere. So the electric field on anywhere outside is going to be based upon this formula, KQ over R squared. So that means that as I get farther away, the electric field is going to get less and less and less in magnitude based upon the R squared. So what that means is that the electric field is not equal to 0, so answer A is wrong. Letter B says the electric field of 1 is greater than E is greater than E2. Well, that one is looking pretty good so far. C says the electric field is the same as the electric field 1. That's not true because it's going to be based upon this R squared. The further away I get, it's going to get weaker. And D says that 2 will be greater than 1 and E will be in the middle, but that's not correct because 2 is farther away. And again, because of this inverse square law, then E2 is going to be less. So that leaves us with option B as the right answer for question number 20. Now question 22, we've got a metal sphere with a small negative charge. So it's a metal sphere, it's a conductor, hanging vertically from a light thread as shown in the figure above. It's then brought near but does not touch an uncharged plastic sphere of the same size that's also hanging vertically on the light thread. So now I've got a second one here that's plastic, meaning it's an insulator, and they're brought near each other. Which best shows the two spheres after they have reached equilibrium? Well, this is a case where I have a conductor or I have a charged object that's near an insulator. What happens near an insulator is that the charges will polarize. Since the metal is negative, what that's going to do is it's going to take each little region of space here and it's going to attract some positive a little bit towards the negative, which will leave a little bit of negative behind. And then the next atoms are also going to have the charge pulled towards the negative sphere, and then that's going to do is leave some more negatives behind. Now I've got the positives, and the positives on the conducting sphere, sorry, on the plastic sphere, and they are going to be attracted to the negatives in the metal. So what that's going to do is move the negatives, they're going to move a little bit over to the right in order to be closer to that positive. So what we're doing is the metal is going to, the charge is going to flow, and on the plastic, the charge is going to polarize, and then those two objects will be attracted to one another. So that means that since they're A, it just has them hanging still, that's not going to be the case. D has them pushing apart, that's not going to be the case. B shows a net positive charge on the plastic, and we know that's not the case because all that's going to happen is the charge is going to polarize, so that's not true. But C has the negatives closer, being pulled to the right in the metal sphere, so that's good. And on the plastic, we have the charge separation, the polarization, and so C is looking like a really good answer for that problem. All right, question 30. A hydrogen atom is isolated in a vacuum chamber. The electron is now separated from the proton and moved to a distance 1 centimeter away. We're going to let Fg be the magnitude of the gravitational force between the proton and the electron, and let Fe be the magnitude of the electric force between the proton and the electron. How does the ratio change as the particles are separated? The electric force is given by Coulomb's law, K Q1 Q2 over R squared. The gravitational force is given by Newton's law of universal gravitation, G M1 M2 over R squared, and we're looking for the ratio of those two. So if we're dividing the force gravity by the force electric, well, the force gravity is G M1 M2 over R squared. If we're dividing by a fraction, we can flip the fraction and multiply, so we get R squared over K Q1 Q2. Now you should notice that R squared is going to completely cancel out. That means the ratio is going to be G M1 M2 divided by K Q1 Q2. G is a constant, the mass of the proton and the mass of the electron don't change. K is a constant, and the charge on the electron and the charge on the proton don't change. What that means is that the force gravity to force electric does not change, so it doesn't become larger, it doesn't become smaller, and it's not that it cannot be evaluated, but it is the same non-zero value for all separations. So A is looking really good there. Because we don't have a zero value, we don't have things canceling out completely, but we do see Gm1 M2 over Kq1 Q2 is going to be some number regardless of how far away those particles are. So answer A. All right, question number 34. We have three charges here on the axes. We have +4 microcoulombs at 0.2 on the y-axis. We have -5 microcoulombs at 0.3 on the x-axis. And we have 2 microcoulombs at the origin. And it's asking for the magnitude of the electric force exerted on the object located at the origin. So what we need here is to take the +4 and the +2 is going to yield some force in the downwards direction. And then the -5 and the +2 is going to yield some force in the rightwards direction. And then what we're looking for is the resulting force from those two, which will be pointing somewhere down and to the right. And so that's going to make a right triangle, so we're going to have to Pythagorize those two forces together. Well, I'm going to label the charges Q1 for the +4 microcoulomb, Q2 for the +2 microcoulomb at the origin, and Q3 is the -5 microcoulomb out on the x-axis. So the force in the y direction is going to be Kq1 Q2 over the distance between 1 and 2 squared. The force in the x direction is going to be Kq2 Q3 over the distance between 2 and 3 squared. Jumping ahead, plugging in some numbers. So Kq1 Q2, that's 9 times 10 to the 9th times 4 times 10 to the minus 6th times 2 times 10 to the minus 6th divided by 0.2 squared gives me 1.8 newtons. And the force in the x direction is 9 times 10 to the 9th times 2 times 10 to the minus 6th times 5 times 10 to the minus 6th divided by 0.3 squared gives me 1.0 newton. I didn't plug in a negative because we've already taken care of the direction with the arrows and knowing that a positive and a negative will attract to the right. So I've got a force in the y direction and I've got a force in the x direction. And so what I have is 1.8 newtons this way, and I've got 1 newton this way, 1.0 newtons this way. And therefore, if I want to find the combined force that way, what I can do is slide the 1.8 over to the right, and now I've got a squared plus b squared equals c squared. And so when we Pythagorize those together, 1 squared plus 1.8 squared square root gives me 2.059 or 2.1 newtons, which looks like answer C right here. That's funny because a squared, b squared, c squared, I had C equals, but yeah, so C over there. All right, this next one, 132, says an isolated point charge plus Q is located at a distance d to the right of point P as shown above. The point charge then moved a distance less than d. So it doesn't say what direction, but which movement will cause a change in the direction of the electric field at point P. So we know that for a positive charge, the electric field at some point is always going to point away from that positive charge. Now, if I picked a point that's closer, then the field is going to be bigger. If I pick a point farther away, then it'll have less field because the magnitude of the electric field, of course, is kq over r squared. So the further away I get, the weaker the electric field is. But as far as the direction, it's directly away from the positive charge. So right now, when plus Q is located at distance d away from P, we know that the electric field is pointing directly away from that positive charge. So in order to change the direction of the field, if I just move that charge anywhere along that axis, that x-axis, it's going to be the same direction as long as I don't get closer than P. It's going to get bigger and bigger, but if I moved it to the other side, then it would be pointing in the other direction. But I'm moving a distance less than d. So moving towards the left and towards the right are not going to give me any change in the direction. But if I were to move the charge down or up, then if I move it up, then my electric field is going to be in that direction. If I moved it down, the electric field would be up in this direction. So both of those would change the direction of the electric field. So towards the top or towards the bottom of the page. I think you heard my dog there, but that's okay. Question 133. 2-point charges Q1 and Q2 of equal magnitude, that's going to be key, are at the vertices of an equilateral triangle as shown above. The sign of each of the charges is unknown. A positive point charge is placed at the vertex P and released from rest. Which of the following shows possible direction of the initial acceleration of the positive charge? Now, I have Q1 and Q2. So what if it was a positive and a positive? Let me draw that. So here's a positive, and what's going to happen to another positive up here? Well, if it's positive and a positive, that's a positive, then this one is going to go this way. This one's going to give a force in this direction. Those two will combine to a force straight up. So if 1 and 2 are positive, then I place a positive, then it's going to be net force straight up direction. If instead I had Q1 and Q2 were both negative, then what I'm going to have is, let's draw that, if I have a negative and a negative, and then I have point P. Well, if I placed a positive there, let's make it red, if I placed a positive there, then the negative will be attracting the positive, this negative will be attracting the positive, and those two vectors would add up straight down. So I have a straight up and a straight down as two possibilities. And then if I had a positive and a negative, so let's erase this top one and let's take another look at it. Let's get rid of that as well. If I had a positive charge here and a negative charge here, and then up top I placed a positive charge, then the positive and the positive will cause a repulsive force, but the negative and the positive will cause an attractive force. And so the up to the right and the down to the right would lead to a net force directly to the right. So I have three options. I could have straight down, so that's a good option. I could have Straight to the right, that was another option. If I swapped the positive and the negative here, then I would have a negative here and a positive here. And if I put a positive charge there, the positive would repel it, the negative down here would attract it, and those two would add directly to the left. So that makes option D look good. But in no case would I have straight towards one charge or straight towards the other charge. So this one is no good and this one is no good. But I can see options for B and D. B would be if I had a negative and a negative, and D would be is if I was attracting it this way but repelling it with a positive over here. So B and D are the good answers to question 133. This next question, I'm back to number 2. It's a different test actually, but it says a small amount of charge is placed at both an isolated conducting sphere and an isolated insulating sphere. For both spheres, the charge is added at a small area at the top of the sphere. After a few seconds, where on each of the spheres is the charge that was added? Well, on the left, I have a conductor. If I put a charge on one point on the conductor, what's going to happen is that charge is going to try to get away from itself, and it's going to wind up distributing around the entire surface of the conductor. So on the conducting sphere, it's going to be spread all over the surface. So either C or D are correct. On the insulating sphere, if I place the charge right on the top, it's going to stay right on the top because the insulator does not allow the charge to move. So the insulating sphere is going to be at the top, And so this turns out to be answer C is going to be the answer that has the right answer for both. All right, for this question, we have the figure showing the three objects that have charges negative 4Q, plus Q, and minus Q. They're held fixed on the axis, and the magnitude of the electrostatic force exerted by object Y on Z is F. So, so that means that, let me draw this. So it says the force by object Y on object Z is F. What that means is that because of Newton's third law, if that's the force on Z because of Y, then Y is going to have a force on it in this direction from Z, also of magnitude F. And so again, Y is positive, Z is negative, X is 4 times as negative. So now, since the distance between Y and Z and the distance between Y and X are the same, they're both distance A and negative A. What that means is that we have to figure out what is going to be the force of X on Y if the charge is 4 times as much. Now, the magnitude of the force is K Q1 Q2 over R squared. So the R is the same, but what we're doing is one of those charges is going to be 4 times as much. What that means is that the force from X on Y is going to be 4 times as much as the force of Z on Y. So if that's a force to the left of F, then because of X, we're going to have a force to the right of 4F. And so if I have 4F to the right and just F to the left, what that means that net force is going to be 3F to the right. So that's going to be answer C. All right, this next question actually is just a circuits question. It doesn't involve some of the electric field stuff that we've been doing, but let's answer it anyway. Here it tells us the current in ammeter A1 is 10 amps. So, sorry, is 1 amp. So I've got 1 amp of current flowing through A1, and I've got 0.6 amps flowing through A2, and then the two resistors labeled R are identical. So what are the currents in R2 and in each of the resistors labeled R? Well, the first thing to know is that if 1 amp is coming to the left, then I have 1 amp going up this way, coming around this way, going through R1. So coming into this junction is 1.0 amps. What that means is that it's going to split between that junction, between this branch and that branch. So if 0.6 amps goes to the right, then I know 0.4 amps is going to go down through R2. So R2 has got to be 0.4 amps. So one of these two is going to be correct. A and B clearly are wrong. So now we have to figure out what is the current in each of the resistors labeled R. Since those are equal resistances, then the current is going to split equally along the two paths. So if 0.6 amps comes in, then I'm going to get 0.3 amps through each of those resistors. So that is going to be 0.3 amps. which gives me answer C as being my correct answer for this problem. Okay, now we've got a capacitor problem. So a 25 ohm resistor and a 100 ohm resistor are connected in a circuit with a third resistor of unknown resistance and a capacitor of unknown capacitance and a battery of unknown EMF. So we've got a bunch of unknowns. After a long time, the potential difference across the 25 ohm resistor is measured to be 4 volts. So after a long time, the voltage from here to here, that voltage is going to be 4 volts. So the question is, what is the EMF of the battery? Now, after a long time, we know that the capacitor is going to act like an open switch. It's going to be fully charged. So what we're going to do is we're going to ignore this section of the circuit for now. So if the 25 ohm resistor has 4 volts, then the 100 ohm resistor, the current here, is just going to be flowing around the circuit. So it's going to be going out of the battery, through the 25 ohm resistor, coming down, making the turn, going through the 100 ohm resistor, coming back through this resistor, and up into the battery. Now, I could figure out if this is 4 volts, then I know that across the 100 ohm resistor, since it's the same current, and V equals I times R, then I know that the voltage across the 100 ohm resistor is going to be 4 times as much. So this is going to be 16 volts across the 100 ohm resistor. So 16 volts at the 100 ohm resistor. But if I want to find the EMF of the battery, then I really can't figure it out because I don't know the voltage across this resistor. So it turns out that the EMF of the battery cannot be determined without knowing the value of R. So that's going to be the answer to that problem. For this question, we have a positive charged particle moving horizontally entering in a uniform electric field. So just drawing that again, what I have is an E field pointing straight down between those plates. And then we've got the positive charge flying in. So the top plate is charged positive, the bottom plate is charged negative, and we have an electric field directed straight down. This is just like a projectile motion problem with a horizontal projectile. What's going to happen as soon as that charge enters the field, it's going to have a force directed straight down. And so there is no acceleration left or right because it's moving perpendicular. So because there is only a force in the downward direction. So there is no force left or right. So that means in the x direction, it's going to maintain a constant velocity because there's no acceleration in the x world. But in the y direction, it's got an acceleration straight down. So that means that it's going to accelerate straight down in the y world. So if I want to know the x and y positions as a function of time, the x position is going to be increasing because it's going to start to the left and move to the right. So the x position is going to be increasing with respect to time. So that's going to be either C or D because x is not constant, which is what B and A are saying. So actually the x position is not constant with respect to time. It's going to be increasing because it's going to start at a low value and get to a high value according to this axis. The y position is going to be starting at some value and getting lower and lower and lower with respect to time, but it's not going to do so at a constant value. Instead, it's going to do so at an accelerating value. So that means that D is not going to be correct, and C is going to be the answer that we're looking for. All right, this problem says an initially uncharged electroscope. Let's stop right there. What an electroscope has is typically it has a conducting top, it has conducting strings, and 2 little conducting, in this case, spheres. There are other ones that are like a gold foil electroscope that'll just have 2 pieces of foil that are hanging down. And if they become charged, they're going to repel each other. Same thing about these spheres. If they're charged, they're going to repel each other. Now, in this case, let's say we brought a positively charged rod near the top. What that positive charge is going to do is it's going to take some of the negative charges that are on the strings and on the rod, and it's going to attract them up towards the positives. And so if you have the negatives flowing up, what that's going to do is it's going to leave positive charges behind. Those 2 positive charges will have a repulsive force on each other, and they will cause separation. If instead you bring a negatively charged rod, then that negative charge will repel some of the electrons that are sitting on the string and on the spheres. And with the repulsion of those electrons, then I'm going to get a negative charge on this sphere and a negative charge on this sphere, and the negative and a negative again will repel each other. So in this problem it says an initially uncharged electroscope consists of two thin 50 centimeter long conducting wires, so we know the distance there, attached to a cap with a 25-gram conducting sphere attached to the other end of each wire. So we're bringing a charged rod. It doesn't tell us whether it's positive or negative. Close to but not touching the cap, the spheres separate a distance of 30 centimeters. So what we have is, we know this is 50 centimeters. We know that the separation between the two spheres is going to be 30 centimeters. So that's going to be 15 centimeters on this side and 15 centimeters on this side from where they connect. I'm just drawing one of them. With the 50 and the 15, we probably could figure out these angles if we needed to. And we will need to if we actually were going to do the math. Because if we look at that charged sphere is going to have a gravitational force down this way. It's going to have a force of tension up in this direction, and it's going to have a force electric repelling from the other charged sphere. So since we know the mass, 25 grams, we can figure out the force of gravity. If we know the force of gravity and the angle, what we can do is we could figure out what this force of tension is, because we have the three forces that are balanced. So that means that the force of gravity plus the force electric are going to equal a force in this direction, which is going to be equal to the force of tension in that direction. So we can draw a right triangle in order to figure out what the force of tension is using some trig. I won't go through it because we actually don't need the numbers. Then if we have that force of tension, we can easily figure out the force electric, again using that trigonometry. So now I can know the force of gravity, the force of tension, and the force electric. So the question is, what can be determined about the induced charge on each sphere? Well, if I know the force of electric and I know the distance between the two spheres is a total of 30 centimeters, then what I can do is I can calculate the magnitude of the charge, because that electric force is going to be K Q1 Q2 divided by R squared. And I know the radius, and I know the Coulomb's constant, and I know the force electric. That means that I can figure out the charges. So I definitely can figure out the magnitude of the charge. This one says not the magnitude, so B is clearly wrong because I can figure out the magnitude. C says both the magnitude and the sign. Well, I can figure out the magnitude so far. And D says nothing can be determined about the induced charge. That's not true because I can already said I can figure out the magnitude. Now the question is, can I figure out the sign? Well, earlier on when we described what was going on up here, we showed an example where if this is negative, then both charges will be negative and they'll repel. If this were positive, then both charges would be positive and they'd repel. So based upon the conditions here, we cannot figure out the sign because both would behave the same if they were positive or negative. So this means that I can find the magnitude, but not the sign. So A is going to be the answer to question 17. Now we've got several questions about this situation where we've got two identical spheres. They're hanging down. They're initially 10 centimeters apart. And then they get charged. So A gets negative 10 microcoulombs. So I've got negative 10 microcoulombs over here. And then B gets a charge of negative 20 microcoulombs. Now you can see that they are going to be repelling each other. So that means that their new position is going to be repulsive, so that they're going to move out a little bit. Each one of those spheres is going to have a force gravity on it, and each one of those is going to have a force electric on it, and each one of those is going to have a force tension on it. So the other one is going to be this way with a force of tension. It's going to have a force of gravity, and it's going to have a force electric. So question 25 says, let Y0 be the vertical position of the uncharged spheres, and then which correctly ranks the new vertical positions of the spheres respectively. So the question is, will the sphere A go higher or lower or neither with sphere B? Now, we know that the force of gravity on them is going to be the same. What about the electric force? Since this is a negative 20 and this is only a negative 10, will they have different electric forces? Well, actually not. The force electric on both of them is going to be K Q1 Q2 over R squared. we know that the distance is the same, and the Q1 times Q2, actually, even though they're different charges, when I multiply them together, I'm going to get the same value for the force electric because K is also constant. So force electric and force electric are going to be the same. That means that since the forces on them are the same, what we're going to get is they're both going to be pulled the same amount, and therefore they're both going to reach the same angle, and they're both going to reach the same height. So A and B are going to be at the same height. So, and they're both going to be higher than they used to be. So the height of A is going to equal the height of B, and they're both going to be greater than 0. So A is our answer to question number 25. Next, we're asked about the electric field, and the electric field is given as KQ over R squared. So we know that the charge of A is going to be less than the charge of B because A is -10 and B is -20. That means the -20 is creating a stronger electric field than the -10. So B will create a stronger electric field near A than A creates near B. So I know that the electric field of B is going to be greater than the electric field created by A. Now let's look at the questions. We want to find the comparison of them, EB and EA. So EB is the magnitude of the electric field produced by B. So yeah, I have labeled them right. This says A is less than B. So A says A is less than B because at the same distance away from a point charge, the larger magnitude charge will produce a larger magnitude electric field, and B has twice as much charge on it. That's looking really good. B says EA equals B because Newton's third law. Well, third law is about forces, not about electric fields. And so that is not going to be true. The forces are the same, but the forces are the same because I have a bigger charge in a smaller field and a smaller charge in a bigger field, and those two are going to be the same. But the electric fields are not the same, so B is not correct. C also says the electric fields are the same. We know that's not correct. And let's see. Yes, it is true that Q1 times Q2, by the way, 1 over 4 pi epsilon naught, that's the same thing as K. So this is giving me an equation for force. And so yes, Q1 and Q2 are the same, but this is just talking about the force, not about the electric field. So this is not true. And D says A is greater than B, but we know that already that B is greater than A. The larger charge will produce a larger field. That's true. But A has more charge in it because -10 is greater, less negative than -20. No, what we're talking about is the magnitude of the charge, not the amount of the charge. So even though it's negative and negative, that's not what we're talking about because whether it's a +20 or a -20, the magnitude of the electric field will be bigger, and that's what we're looking for. So clearly, answer A is what we got here for question number 26. For question 27, it says, consider a system defined as only spheres A and B. So what that means is that we are not worried about the gravitational potential energy because then we'd need the Earth in the system in order to store gravitational potential energy. So we're only comparing the electric potential energy initially and after they reach their new equilibrium position. So when we charge them, when they're hanging vertically and then when they are at their new position. So hanging vertically, the electric potential energy is given as K Q1 Q2 over R, simply R. Now, when they're closer together, R is smaller, so U is bigger. And then when they separate, R is bigger, so U is smaller. So what happens is the potential energy of the system has gone down because the charges are farther away from each other. So let's see which answer that is. A says the potential energy of the system has remained the same. That's not true. B says the potential energy has increased. That's not true. We know the potential energy has decreased. C, the potential energy has increased. Nope. D, the potential energy has decreased because the charged spheres will repel each other rather than attract, reducing the energy stored in the electric field. Yeah, and when they repel each other, they move away from each other, and so it's a little bit questionable as, they repel rather than attract, reducing the energy. It's because they've moved apart from each other that it's reduced the energy stored in the electric field. So of the answers, D is going to be the best answer, although I wouldn't have worded it that way. All right, one more question on this. Question 28, consider a position P located halfway between the spheres in their new equilibrium configuration. So I've drawn P halfway between A and B, A with a negative 10 microcoulomb and B with a negative 20 microcoulomb. So we've got spheres A and B. Now, which of the following indicates whether the electric potential at this position is positive, negative, or zero, and explains why? Electric potential is KQ over R, and it's going to be the sum of all the KQ over Rs. Electric potential is also a scalar, so we can think if it's a positive electric potential, then it would take positive work to bring a positive charge in from infinity, because we would be pushing that positive charge towards that position the whole time. And since the potential energy is the charge times the electric potential, a positive charge and a positive electric potential would give me positive energy. So electric potential would be positive near a positive charge and negative near a single negative charge. In this case, I have a negative 10 and a negative 20. Both of those would contribute to a negative electric potential because R is a positive value, both of the Q's are negative, and K is a positive constant. So that tells me that the electric potential is going to be negative at that point, because if you think of taking a positive charge from infinity and moving it to point P, what I'm going to have to do is I'm going to have to hold it back from its attraction to the negative 20 and hold it back from the attraction to the negative 10. So I'm going to have to apply a negative force on it the whole time, doing negative work all the way to point P. So it's not zero, it's not zero. We don't even have to read more about this. C says positive, and that's not true. D says negative, that's looking good, because both negatively charged spheres contribute to a negative electric potential to the total. That's going to be true because both of them will have a negative Q and a positive R, because R is just a distance. It doesn't have a vector quantity to it. And so since Q's are negative, its contribution to the potential is going to be negative. So D is a good answer for question 28. I think we are on our last slide. Yes, here is our last slide. All right, this is a good question. We have two electrically neutral conducting rods near a negatively charged sphere as shown in the figure above. Rod 1 is touched to rod 2 for several seconds, and then the rods are separated. The rods are then both removed from the vicinity of the charged sphere, which is the following is the resulting net charge on each rod. So if you think about it, we have that negative sphere. If I just had a single rod there, what's going to happen is that charge is going to repel some of the negatives in that conductor over to this side, and it's going to attract some of the positives over to this side of the rod. Now, if that was a single rod, you would get a charge separation, and then if you moved it away, it would be back to neutral. But if I take this, and instead of having a single rod, if I had the two rods touching together, the same idea will happen as if I had a single rod. So what I'm going to get is I'm going to get a flow of electrons to the right away from the charged sphere. Now, if I get rid of the charged sphere, so let's get rid of the charged sphere. Now, just momentarily, I had those rods, but they were separated. So let me just erase this for a second. So now those two charged rods that did have the charge flowing in them are separated and then moved away. Well, this rod on the left is going to have a net positive charge, and the rod on the right is going to have a net negative charge after I've moved them apart. And this is also assuming that they're not anywhere near each other, because they would still have a net positive and net negative. If they're close to each other, then I get some more polarization of that charge. So in the end, rod 1, this is number 1, is going to be positively charged, and 2 is going to be negatively charged, because when they are connected, some of the negative charge will flow to the right, and that will leave positive behind on the left. So let's see, A says 1 is positive and 2 is negative. Oh, no, sorry, that is our answer. That is our answer. 1 is positive and 2 is negative. B says 2 is positive and 1 is negative. That's not true. C says they're both negative. That's not possible. And D says they're both uncharged. That's also not possible. So what we have is answer A. Hope that was helpful, and we'll talk to you later sometime.